Welcome to week 2. Week 1 may have been a little bit busy. This was because we tried to give you at least a flavor of what you can expect in the rest of the course. You were introduced to vectors and operations with vectors, as well as notation. We then moved on and talked about slicing and dicing and how this helps us express algorithms without worrying about indices, and how to then translate algorithms expressed with slicing and dicing into code. This week we're switching gears a little bit. We will start by discussing rotations in 2 dimensions and how a function that captures a rotation has very special properties. Functions that have those properties are known as linear transformations. You will learn how to prove properties of linear transformations, and that will then help you make the connection between linear transformations and matrices. Let's get started. To motivate linear transformations, we're going to look at rotating vectors in 2 dimensions. Here we depict a vector in 2 dimensions. And if we rotate that vector through an angle theta, then we get a new vector. So, we can let the function r sub theta of x denote the function that transforms vector x into the rotated vector. Let's have a look at some special properties of this function. We have learned how to scale a vector. Alpha times x is merely x with its length scaled by a factor alpha. If we first scale vector x by factor alpha and then we rotate it, we get this vector right here, r sub theta of alpha times x. If we take the vector x and we first rotate it, then we get this vector right here, r of theta x. And if we then scale it by alpha, then we get this vector right here, alpha times r sub theta of x. If you look at it very carefully, what you notice is that if you scale the vector x first and then you rotate it, you get exactly the same vector as you would if you take vector x and you rotate it through angle theta first. That gives you this vector right here, and then you scale it. Interesting. What you notice is that you can rotate the vector x first and then scale it, or you can scale it first and then rotate it. Either way, you get the same answer. Let's look at another property. Here we have a vector x, and here we have a vector y. Last week we learned how to add vectors x and y. You use the parallelogram method, and it becomes one of the diagonals. If we first add x to y and then we rotate it through angle theta, then we get this vector right here, denoted by r sub theta of x plus y. I wonder what would happen if we first rotate x and we rotate y, and then we add the result of that together. Well, here we have x, we rotate it through angle theta. Here we have y, we rotate it through angle theta. We create the parallelogram of the results, and lo and behold, we get a vector that is identical to the vector that we got if we added x and y together first and then rotated it through angle theta. Okay. So here we first add it and then we rotate it. Here we rotate first and then we add. And we can go back and forth. Either way, we get the same answer. So, what we notice about rotating vectors is that you can add the 2 vectors first and then rotate, or you can rotate them first and then add. Now, it could of course be that this is simply because of the specific examples that I chose. However, you can use high school geometry to show that you can stretch first and then rotate, or rotate first and then stretch and get the same answer. Mathematically, we can denote that by this. Here we stretch x first and then we rotate. Here we rotate vector x first and then we stretch. Also, with high school geometry, you can show that if you add the vectors first and then you rotate, you get exactly the same answer as if you rotated x first, rotated y, and then added the results of those together. A vector function L is a linear transformation if you can scale first and then transform, or transform first and then scale. Okay, so here we have function L, vector function L, and if we first scale x, we get exactly the same result as if we first transform x and then scale. Also, you can transform first and then sum, or sum first and then transform. Mathematically, we can say add the vectors first, then transform, or transform first and then add. So, rotating a vector in 2D through angle theta is an example of a linear transformation. For the rest of this week, and as a matter of fact for the rest of this course, we will be talking about linear transformations a lot.